That is voltage. And how does voltage work? Voltage. Voltage, also known as electric potential difference or electric potential, is a measure of the electric potential energy difference per unit charge between 2 points in an electric circuit. In simpler terms, it's the push that causes electric charges to flow through a conductor from a point of higher voltage to a point of lower voltage. Voltage is the driving force behind the movement of electric charges and the flow of electric current in a circuit. Here are a few key points to understand about voltage. Electromotive force, EMF. Electromotive force, EMF, is a term that refers to the potential difference or voltage produced by a source such as a battery, generator, or any other device that can provide electrical energy to a circuit. Despite its name, EMF is not a force in the mechanical sense, rather, it's a measure of the energy supplied by the source to drive electric charges around a closed circuit. Here are some key points to understand about EMF. Energy supplier, EMF represents the energy per unit charge supplied by a source to maintain a potential difference across a circuit. It's the work done on each unit of charge as it moves through the source, like a battery. Voltage source, EMF, is often associated with voltage sources like batteries. When a battery is connected to a circuit, it establishes a potential difference between its terminals, creating an electric field that can push charges through the circuit. Unit of measurement, the unit of EMF is the volt, V, which is the same as the unit of voltage. This is because EMF is essentially a type of voltage, specifically the voltage produced by a source. Internal resistance, real-world voltage sources like batteries may have internal resistance due to the materials and processes within them. This internal resistance can cause a voltage drop within the source itself when current flows, leading to a slightly lower effective EMF across the terminals. Closed circuit EMF is relevant in a closed circuit, where charges can complete a full loop and return to the source. In an open circuit, where there's no complete path for charges to flow, EMF doesn't result in a current. Conservation of energy, the energy provided by the EMF is used to overcome the resistance in the circuit and perform work, such as lighting a bulb, powering a motor, or charging a capacitor. Direction, EMF has a direction associated with it, determined by the positive and negative terminals of the source. The electric field generated by the EMF pushes charges from the negative terminal to the positive terminal within the circuit. In summary, electromotive force, EMF, is the driving factor behind the movement of electric charges in a circuit. It's the energy per unit charge supplied by sources like batteries to create a potential difference that causes current to flow. While EMF is often used interchangeably with voltage, it specifically refers to the voltage produced by an energy source. Potential difference. Potential difference, often referred to simply as voltage, is a fundamental concept in electricity that represents the difference in electric potential energy between 2 points in an electric circuit. It's the driving force that causes electric charges to move from one point to another, creating an electric current. In essence, potential difference is what motivates charges to flow in a circuit. Here are some key points to understand about potential difference. Energy difference. Potential difference is a measure of the energy per unit charge required to move a charge from one point to another within a circuit. It's the work done to move a charge against an electric field. Unit of measurement. The unit of potential difference is the volt, V, which is a derived unit in the International System of Units, SI. 1 volt is equal to 1 joule of energy per coulomb of charge. Voltage between 2 points, potential difference is always measured between two specific points in a circuit. It indicates how much energy each unit of charge gains or loses when moving from one point to the other. Polarity. Potential difference has polarity, meaning it has a positive and a negative side. The point with higher potential energy is the positive side, and the point with lower potential energy is the negative side. Voltage sources, such as batteries or generators, establish potential differences across a circuit. They provide the energy necessary to create an electric field that can push charges through the circuit. Voltage drop. As electric charges move through various circuit components, such as resistors, capacitors, and inductors, there can be a change in potential energy, leading to a voltage drop across those components. Analogy to gravity. An analogy often used to explain potential difference is that of a ball rolling downhill. The ball gains kinetic energy as it moves from a higher gravitational potential, higher elevation, to a lower potential, lower elevation. Similarly, charges gain energy as they move from a higher voltage point to a lower voltage point. Circuit workings. Potential difference is responsible for the flow of current in circuits. It's what makes electrons move through conductors, creating the electrical current that powers devices and systems. In summary, potential difference, or voltage, is a measure of the energy change per unit charge between 2 points in a circuit. It's a crucial concept in understanding how electric circuits function and how electrical energy is transferred from a source to various components within a circuit. Voltage sources are devices or components in an electrical circuit that provide a potential difference, or voltage, across their terminals. They are responsible for establishing an electromotive force, EMF, that drives the movement of electric charges and the flow of current in a circuit. Voltage sources play a fundamental role in powering various electronic devices, systems, and circuits. There are two main types of voltage sources. Ideal voltage source. An ideal voltage source is a theoretical concept that provides a constant voltage regardless of the current drawn from it or the load connected to it. In other words, it maintains a fixed potential difference across its terminals regardless of the conditions. An ideal voltage source is often represented by a simple symbol, usually a circle with a plus and minus sign, and a voltage value, such as V. In practice, real voltage sources have limitations and internal resistance that can affect their performance. Real voltage source. Real voltage sources are physical devices that generate a potential difference but may have practical limitations. Examples of real voltage sources include batteries, generators, power supplies, and solar panels. Batteries are common examples of real voltage sources used in portable electronics and various applications. Generators and power supplies are used to provide power in larger scale systems, such as industrial machinery and power distribution networks. Voltage sources are typically characterized by their voltage output and their internal resistance. Voltage output, this is the nominal or rated voltage that the source is designed to provide. It's the potential difference across the terminals of the source when no current is drawn from it. Internal resistance. Real voltage sources, such as batteries, have internal resistance due to the materials and design of the source. This internal resistance can cause a voltage drop within the source when current flows, leading to a decrease in the effective voltage across the terminals. Voltage sources are used to power various types of electronic devices and systems, ranging from small-scale applications like smartphones and laptops to large-scale applications like power plants and electrical grids. They provide the necessary energy to move charges and create electrical currents, enabling the functionality of numerous technological advancements in modern society. Polarity refers to the direction and orientation of a physical quantity in a circuit, particularly in relation to electric charges and the potential difference, voltage, between 2 points. Polarity is a crucial concept in understanding how electric circuits work and how components are connected within them. In the context of electricity and circuits, polarity mainly applies to two aspects: voltage and the direction of current flow. Polarity of voltage. Voltage is a measure of electric potential energy difference between 2 points in a circuit. Polarity in terms of voltage indicates which terminal of a voltage source, like a battery, is at a higher potential energy and which is at a lower potential energy. Polarity helps determine the direction in which current flows through the circuit. In terms of voltage, the terminal with higher potential energy is considered the positive terminal. The terminal with lower potential energy is considered the negative terminal. For example, in a battery, the longer terminal might be designated as the positive terminal, and the shorter terminal might be the negative terminal. When you connect the positive terminal of a battery to the negative terminal of another component, you create a potential difference that drives current flow. Polarity of current flow. Electric current is the flow of electric charges, usually electrons, through a circuit. Polarity in terms of current flow refers to the direction in which the charges are moving. It's important to be consistent in defining the direction of current flow because it affects how we interpret the behavior of components in a circuit. In terms of current flow, conventional current flows from the positive terminal of a voltage source to the negative terminal. This convention was established before the discovery of electrons and is the way current direction is typically represented in circuit diagrams. Electron flow, on the other hand, is the actual movement of electrons and is in the opposite direction to conventional current. Electrons move from the negative terminal of a voltage source to the positive terminal. It's important to note that while conventional current flow and electron flow are opposite in direction, the principles governing their behavior in circuits are the same. The choice of which convention to use depends on context and historical conventions. Understanding polarity is crucial when connecting components in a circuit to ensure that the intended direction of current flow is maintained and the circuit operates as desired. In many circuit diagrams and schematics, symbols are used to represent the polarity of components and connections, making it easier to design and analyze circuits. Voltage drop refers to the reduction in voltage that occurs as electric current flows through a component, conductor, or circuit due to the inherent resistance of the material. In practical terms, voltage drop results in a decrease in the potential difference, voltage, between 2 points in a circuit as current passes through a resistance. Here are the key points to understand about voltage drop. Resistance: when electric current flows through a material, such as a wire, resistor, or other circuit components, there is a natural opposition to the flow called resistance. This resistance is caused by factors such as the material's properties and the dimensions of the component. Ohm's law: according to Ohm's law, the voltage drop across a resistor, V, is directly proportional to the current, I, passing through it and the resistance, R, of the resistor. Mathematically, this relationship can be expressed as V equals I asterisk R. Proportional relationship: the higher the current passing through a component with resistance, the greater the voltage drop across it. Similarly, the higher the resistance of the component, the greater the voltage drop for a given current. Energy conversion: the energy that's lost as voltage drop is converted into heat due to the collisions of charge carriers, usually electrons, with atoms in the material. This heat generation can be significant in components with substantial current and resistance. Impact on circuit performance: voltage drop can have practical consequences in electrical systems. For instance, if a long wire with significant resistance is used to connect a device, the voltage drop along the wire might cause the device to operate at a lower voltage than intended. This could affect the device's performance. Minimization of voltage drop: in circuits where voltage drop is a concern, steps can be taken to minimize its impact. This might involve using thicker wires with lower resistance, optimizing the arrangement of components, or employing materials with lower resistance values. Voltage regulation: in power distribution systems, voltage drop is an important consideration to ensure that devices and appliances receive the required voltage for proper operation. Voltage drop calculation: engineers and designers often calculate voltage drops in circuits to ensure that components receive adequate voltage. This involves analyzing the circuit's characteristics, the current flowing through it, and the resistance of the components. In summary, voltage drop is a natural consequence of the resistance present in electrical components and conductors. It's an important consideration in circuit design and power distribution to ensure that devices receive the appropriate voltage and function as intended. Ohm's law is a fundamental principle in electrical engineering and physics that establishes a relationship between voltage, current, and resistance in an electrical circuit. It's named after the German physicist George Simon Ohm, who first formulated this law in the early 19th century. Ohm's law provides a mathematical framework for understanding and predicting the behavior of electrical circuits. Mathematically, Ohm's law is expressed as V equals I asterisk R, where V represents the voltage across a component or circuit, measured in volts, V. I represents the current flowing through the component or circuit, measured in amperes, A. R represents the resistance of the component or circuit, measured in ohms, omega. Here's a breakdown of the law's components and what it means. Voltage, V. Voltage is the electric potential difference between 2 points in a circuit. It's the driving force that pushes electric charges to move from one point to another. Voltage is analogous to the pressure in a fluid system. The unit of voltage is the volt, V. Current, I. Current is the flow of electric charges, usually electrons, through a conductor or circuit. It's the rate at which charges pass a specific point. The unit of current is the ampere, A. Resistance, a. Resistance is the opposition that a material or component offers to the flow of electric current. It's a measure of how much a component restricts the flow of charges. The unit of resistance is the ohm symbol. Ohm's law states that the voltage across a component or circuit is directly proportional to the current flowing through it, and this relationship is moderated by the resistance. In other words, the voltage drop across a component is equal to the product of the current passing through it and the resistance it presents to that current. This law provides a fundamental tool for analyzing and designing electrical circuits. Engineers and technicians use Ohm's law to calculate various circuit parameters, such as determining the voltage drop across resistors, finding the current through different components, and choosing appropriate components to achieve desired circuit behavior. Keep in mind that Ohm's law holds true for linear, passive components within their operational limits. Components with nonlinear behavior, like diodes and transistors, may not strictly follow Ohm's law. Analogizing electrical concepts to fluid dynamics can provide a helpful way to understand these concepts, especially for those who are new to the field of electricity. One common analogy used is comparing electrical voltage, potential difference, to pressure in a fluid system. Here's how the analogy works. Analogous to pressure. In a fluid system, pressure is a force per unit area that drives the flow of a fluid. It causes fluids to move from areas of higher pressure to areas of lower pressure. Similarly, in an electrical circuit, voltage, potential difference, is like the pressure that drives the flow of electric charges, current, through the circuit. Here's a breakdown of the analogy. Voltage, electric potential difference, pressure, voltage represents the electric potential difference between 2 points in a circuit. Just as pressure in a fluid system causes the fluid to flow from high-pressure areas to low-pressure areas, voltage creates an electric field that causes electric charges to flow from high-voltage areas to low-voltage areas. Current, fluid flow, electric current is the movement of electric charges, usually electrons, through a conductor. This movement is similar to the flow of a fluid in a pipe. The greater the pressure difference in the fluid system, the faster the fluid flows. Similarly, the higher the voltage difference in an electrical circuit, the greater the current flows. Resistance, flow obstruction. In fluid systems, resistance can come from factors such as narrow pipes or obstacles that impede the flow of fluid. In an electrical circuit, resistance is the property that opposes the flow of electric current. Higher resistance limits the flow of current, just as obstacles or narrow passages in a fluid system limit the flow of fluid. Ohm's law flow equation. Ohm's law, V equals I asterisk R, can be compared to the equation that relates pressure, flow, and resistance in a fluid system. In fluid dynamics, the flow rate, Q, is proportional to the pressure difference, delta P, and inversely proportional to resistance, R, expressed as Q equals delta P/R. Using this analogy, you can think of voltage as the electrical pressure that drives current flow through a circuit. Just as fluid systems have various components that affect flow, such as pipes and valves, electrical circuits have components like resistors and conductors that influence the behavior of electric current. Remember, while this analogy can be helpful for conceptual understanding, electricity and fluids are distinct physical phenomena with their own unique properties and behaviors.